Now I am testing this cheap mirror, which must produce very cheap energy to be better than solar panels or thermal power plants. My cheap mirror consists of these two parts, and the first part is this primitive reflective film costing 25 cents per square meter. This is the second part, and I spent less than $3 buying these thin steel rods. After installing the film on the mesh of the steel rods, we have a concave mirror, and let's take a look at how it will focus solar radiation. We see that I will have to radically change the design of my mirror to focus the radiation better. Nevertheless, this very bad mirror can give us fire, and let's look at how it will light a piece of newspaper. The paper does not light up immediately, and I had to wait for about 2 minutes while my concave mirror created the fire. I think everyone understands that my goal is not to make fire, and my goal is not to grill a sausage with bacon. My goal is to find the cheapest mirror in the world to replace similar expensive mirrors which make up large solar power plants or produce solar heat with a temperature of several hundred degrees. These beautiful mirrors cost several $100s per square meter, and it is 50 times more expensive than my mirror. Its most expensive part is this mesh. Its manufacturing technology is similar to these fences with a lifespan of several tens of years. Interesting that the wholesale price of similar meshes may be less than $2 or $3 per square meter. Of course, my mirror has many disadvantages, and my experiments should find these disadvantages and eliminate them. However, we know that these traditional mirrors have to turn according to the movement of the sun across the sky. But I will try to create a different type when the mirror is absolutely motionless and the sun is accompanied by the movements of this receiver, and I plan to describe this new type in my future videos after a few experiments. My goals are fixed by this formula, which requires the cost of our solar heat at the level of half a cent per kilowatt hour, and it is approximately 10 times cheaper than the cost of heat from natural gas. For example, here we can see that I will aim for the total cost of making and installing my absolutely motionless mirror less than $10 per square meter. Of course, this annual heat production will be significantly higher for that traditional case of turning mirrors, but the need to turn our mirrors will increase this cost. Let's look at this receiver, which has these two parts. This is its absorber. Now I am showing one of my experiments when cold water goes through this absorber and comes out here. We see that solar energy has heated the water to a temperature of 36 degrees Celsius. At the same time, the temperature of the cold water at the inlet of the absorber is 14 degrees, and we understand that the movement of the water through the absorber increases the water temperature by 22 degrees. This is a similar experiment on heating the water with my receiver. Here we can see that the receiver is covered with a transparent plastic sheet, which is needed if the heating temperature is several hundred degrees, and it should not be the water but thermal oil, similarly to the solar power plants. We know that solar energy heats the oil inside these tubes to temperatures of 300 or 400 degrees Celsius. Then the hot oil produces steam for a turbine with an electric generator, or the thermal energy of the oil is transferred to the inside of similar heat storages. Then, in the evening and at night, the thermal energy produces steam for the same turbine. So, our cheap mirrors can heat thermal oil to generate cheap electricity, which can be generated both day and night, 24 hours a day, thanks to heat storages. Now I will show an experiment to measure the maximum heating temperature. At first, this situation lasted for about 20 minutes, and let's look at what happened next. I must clarify that my absorber is coated with ordinary black paint. We understand that the maximum heating temperature will be higher if we use a selective coating of our absorber, similar to the coating of such solar collectors. We see that the maximum temperature of heating my black paint is more than 300 degrees Celsius. Nevertheless, we understand that I have to make a new mirror and absorber because I want to reach the maximum heating temperature of more than 500 degrees Celsius. My new mirror should focus solar radiation radically better, and the overall dimensions of my new absorber should be smaller. I repeated this experiment several times, and let's look at the transparent covering of the receiver after my experiments with heating to temperatures greater than 300 degrees. This is polycarbonate, and we understand that it must be a more refractory material if you want to heat oil with a temperature greater than 300 degrees Celsius. Of course, this reflective film does not have a long lifespan, but it is very cheap and its replacement is easy. Nevertheless, our annual cost of film replacement must be consistent with these operating costs, less than $1.25 per square meter, and I remind you that I bought this film at a price of 25 cents per square meter. Interesting that mirrors with a short lifespan do not require regular cleaning, which is a must for long-life mirrors. I am planning to make a new video on the topic of the lifespan of my mirrors after several months of testing my mirror with wind, snow and other weather phenomena. I have been doing similar testing for 2 years already, and for example it turned out that the lifespan of this mirror is slightly less than 1 year. But if we add this cheap strong film, the lifespan of the reflective film becomes more than 1 year. And this strong film has a long lifespan.